السلام عليكم.
وعليكم السلام. أهلا دكتور.
الله يعطيك العافية. مهندس سارة، كيف حالك؟
وعليكم السلام.
أهلا يعطيكم العافية.
السلام عليكم جميعا، كل عام وانتم بخير.
وأنت بخير، الله يعطيك العافية.
سلامات.
وأنت بخير.
السلام عليكم.
السلام عليكم جميعا، يعطيكم العافية وكل عام وأنتم بخير.
أنا مش سامع، سامعيني؟
سامعينك.
سامعينك دكتور مهند. نعم
احنا سامعينك.
سامع.
يعطيكم العافية جميعا. رح ننتظر بضع دقائق لينضم الجميع ونبدأ ورشتنا لليوم. لا دكتور مهند, we cannot hear you.
السلام عليكم.
هلا وعليكم السلام. أهلا مهندس.
والله طاعتكم للجميع وكل عام وانتم بخير.
أنت بخير.
وأنتم بألف خير دكتور.
وأنت بخير دكتور.
وأنتم بخير. أحد سامعني هلا؟
نعم سامعينك دكتور.
الحمد لله اللي زبطت. وأنتم بخير.
أنت بخير دكتور. أهلا.
كنا حابين نعيد عليكم بعد ما تنتهي المقابلة.
إن شاء الله.
مهندس سارة, بدي أسألك سؤال. تتذكر مرة عملنا كلاشرينج حوالي 5 أيام, برنامج كان تتذكر صح؟ مهندس سارة؟
نعم.
في عملنا مرة البرنامج 5 أيام, كان على كلاشرينج ما كلاشرينج ومش عارف ايش. برنامج كان لمدة 5 أيام تقريبا, متتاليات زي ورك شوب.
نعم.
بس ما وصل
نعم.
شهادة حضور.
5 أيام ورا بعض. دريت بأي من أي فريق؟ إيكوكار؟
دكتور أكثر شو قصتك يا دكتور؟
أهلين دكتور أحمد, كيف حالك؟
عندك شهادة؟
ما حداش أعطاني شيء.
هذا بالأرض ترى عند المهندس أشرف. حكيت ثاني, حكي لك عن الشهادة ثاني. طب الله يسامحك, انت ناسف. هاي الحاجة طلعت على المهندس الثاني.
احنا حابين نحكي, فكان الدكتور حش موجود, ثاني طلع موجود.
مأثر عليك الصيام دكتور أكثم كأنك؟
لا والله الحمد لله رب العالمين, الصيام ممتاز جدا بالنسبة لي. أهلين دكتور أكرم, السلام عليكم. واحد بقول أول شيء.
وعليكم السلام ورحمة الله. رمضان كريم.
الله يحفظكم.
السلام عليكم ورحمة الله جميعا, كل عام وانتم بخير.
انتم بخير
جميعا.
الله يعطيكم العافية.
حياك الله.
طيب أتوقع يمكن So we have like we have Florian with us. So might be sometimes we will want to switch to English, but the Florian, if we talk in Arabic, so maybe you can understand some words. يعني احنا بنرحب فيكم جميعا اليوم، وكل عام وانتم بخير، رمضان كريم، تقبل الله منا ومنكم صالح الاعمال، وان شاء الله يعني صيامكم مقبول وافطارا هنيئا. يعني احنا عارفين هلا اليوم اخر رمضان، بس هيك يبعثوا لنا جماعه جامعه الحسين التقنيه انهم اليوم بدهم يعطوا البرزنتيشن، فان شاء الله يعني تكون الامور ان شاء الله جيده. طبعا احنا we have this training workshop or this capacity building workshop as one of the workshop that was conducted within the Erasmus Plus project EcoCar. The Erasmus Plus project is funded by the European Commissions within Erasmus Plus calls, and we have last years we conducted many training workshops in the field of electric and hybrid cars, and we started this year also with our Jordanian partners. So we have like one training workshop from Jordan University of Science and Technology, another one I think was from Applied Science University, and today we have Al-Hussein Technical University. We'll have Dr. Muhammad Al-Tarifi. He will give us the workshop today, so welcome him and also other colleagues today with us. If Rasha, you can share the presentation. Yeah, we want to give you like very short slideshow, very short like presentation about EcoCar projects. EcoCar projects, as you see that from its name, is like vocational training diploma in electric and hybrid vehicles, EcoCar. So we have like at the University of Jordan. If you can. Yeah, we have like our team, the objective, indicators, and the different work packages. So as you see that the partners in the projects, University of Jordan is the coordinator, and this is like a national project. So we have like 8 universities from Jordan, 5 public universities, and 3 private universities. So we have Jordan University of Science and Technology, Mu'ta University from the south, in addition to Al-Tafila Technical University also from the south. We have Al-Balqa Applied University, in addition to Al-Hussein Technical University, Applied Science University, and Al-Zaytuna University of Jordan. So as you see that we have like 8 universities in Jordan. Therefore, we are expecting the impact of the projects will be very high. In addition, we have like 6 partners from Europe. We have 2 universities from Germany, University of Applied Science and Arts, Ostwestfalen-Lippe. In addition to RWTH Aachen University, also in Germany. We have also one university from Spain, Deusto University, another university from Hungary, Budapest University of Technology and Economics, another university from Greece, National Technical University of Athens, and also the final university or the last university from Italy, University of L'Aquila. So this is the universities that we have. Also from University of Jordan, we have colleagues from 3 departments, mechanical engineering, mechatronics, and electrical engineering departments, in addition to Center of Studies and Consultations at the University of Jordan. And as it was mentioned, the project aims to develop capacities in the field of electric and hybrid cars in Jordan, and bring together and strengthen cooperation between companies, higher education institutions. Therefore, the networking is very important for us to have like partners from the different stakeholders. Also, we'll establish vocational training centers at each Jordanian universities. We'll have also, in the specific objective, as I mentioned, the network between universities and stakeholders is very important. We will have like many training workshops to have capacity building for staff and students in the field of electric and hybrid cars, and will also accredit professional diploma, professional and vocational diploma in the electric and hybrid car. In addition, we will inject some courses within the existing curriculum for bachelor and master programs. In addition, that will also enhance vocational training diploma programs, especially this is the vocational, this is for the students who do not have access to enter the university, which is diploma al-mihani. Also, we have like, exploit the results by organizing, we'll have many workshops. This is technology transfer, and we'll have also improve university enterprise cooperations through many internships in electric companies, electric car companies. Some indicators, I think that this summer we'll have like 8 diploma will be established at 8 universities in Jordan, and courses are integrated in the study programs, and also many workshops will be conducted. Also we'll receive the feedback from the students, in addition to have like this network, regional and international network will be established. Next month we'll have the first training workshop in Europe for within the capacity building, and for those students who will be also enrolled in the program, they will be also have the chance also to get training in Europe. We'll have also the training centers, the lab at each university, and also we have like a website, and currently we are working on the course material, and we'll have e-learning platform will be launched soon. What we said that this is some objectives that we have also want as a general to enhance the teachings, the capacities, the programs in the field of electric and hybrid cars, and this will have also environmental dimensions, since it will also lower emissions, and will have to reduce, will aim to reduce the greenhouse also emissions, and this will help also Jordan to move to be like a hub for electric and hybrid car factories and industry. About what we have till now, we have some universities will have like professional diploma, other will have like vocational diploma, and some universities, especially Al-Balqa and Al-Hussein or Al-Tafile, they will have community college diploma. And we have the different work packages, such as like the network, and the first one was establishing university enterprise cooperation, and this is what we are looking to do. And already we started with this work package, and this will continue till the end of the projects, even that next. And we already now we have the network, and we have about 75 registered members from Jordan and about 13 registered members from Europe in this network. And this is the template to join the EcoCar network. Any company can join this network. Before we prepare the curriculum or the courses, we did like a baseline study, and we did survey. It was like many surveys for students, for staff, for stakeholders, and we analyzed this survey, and the results was the base for our curriculum. And we'll have like many training workshops within capacity building, as you see that this aims to increase the capacity of Jordanian colleagues. And this is an example of the workshop that was conducted, the first one by Aachen University about batteries last year. And also we have another one also within Univac Italy about also introduction to internal combustion engine. We have also a third workshop also from Greece about vehicle dynamics fundamentals, and fourth one from also Hungary about internal combustion engines and hybrid drivetrain systems. Also, Deusto University in Spain gave us also a workshop about vibroacoustic comfort in road vehicles. And last one was from Hochster in Germany about also charge transport in batteries. And then we started with the Jordanian partners this year. The first one was given from Just about EV charging systems and charging infrastructures. Second one was from Applied Science University about modern technology and diagnostics and maintenance of electric vehicles. And today we have this workshop from Al-Hussein Technical University about impact of the topography and traffic on vehicles' energy consumptions. And we hope that next month we'll have also other universities to give more training workshop. So about the labs, soon we'll have like at each university, we'll have like electric and hybrid labs, and hopefully that will have like official opening for these labs. This is an example about the labs that which is available at Applied Science University from our visit to this hybrid labs, electric and hybrid labs. This is also an example about our visits to electric companies that they have also electric cars in Jordan. And we try to link to strengthen this cooperation with the electric companies. Yeah, this is about the new devices that which already started to arrive to the universities, and we hope that within 2 months we'll have all equipments will be available in Jordanian universities. And currently we are preparing the courses. The course material will be ready by the end of this month or next month. And yeah, we'll have like the platform to have this course material. And we'll have also want to have also a certain quality in the projects, and therefore we'll have like continuous monitoring for the implementation of the projects. Yeah, dissemination is very important, and therefore we have like many activities within disseminations. We'll have newsletters, and we'll also, if you have your email with us, we will receive like the newsletter about the projects and the website and other social media. Yeah, for the management, which is coordinated the project by the University of Jordan, this is the project website. You can visit it. This is also the Facebook page. And this is also the YouTube channels that about the projects that we have like some videos on this YouTube channel. So this is like in a brief about EcoCar projects. Now we'll leave you with engineer Sarah Twesi. She will be the moderator for this workshop. So please, Sarah, you can start now.
يعطيك العافية دكتور أحمد. شكرا جزيلا. You were just on time. Please allow me to welcome Dr. Muhannad Al-Tarifi, our presenter for today from Al-Hussein Technical University. Our workshop for today will be estimating the impact of topography and traffic on vehicles' energy consumption. So I will give the floor for Dr. Muhannad Al-Tarifi, and we will start now our workshop. Dr. Muhannad, please start.
Hi, Engineer Sarah. Thank you very much, Dr. Ahmed, and all. Welcome to this workshop. I would like to give the first couple minutes to Dr. Tariq, the program leader from our side in HDU, just to introduce you about our university and what we do. Dr. Tariq, تفضل.
Thank you, Dr. Muhannad. مش راح اطول عليكم. احنا we all know each other. اول شيء كل عام وانتم بخير. طبعا ال HTU is a partner in this EcoCar project. احنا هلا we're investigating to start ان شاء الله vocational degree. هذا التارجت تبعنا هو vocational degree، وعملنا زيارات لمركزين، واحد منهم مركز الحكمه وروكنت. نستنى حتى الورك شوب تخلص، مش الورك شوب تخلص، الماتيريال يخلصوا عشان to compare what we have بالمختبرات المتوفره عندنا بالاتش تي بلس. بشكر الدكتور مهند الطريفي عشان هو راح يعمل الورك شوب هاي، وهو actually he's the expert in بالاتش تي بالالكتريك كارز. هو الشخص المناسب عشان هو actually بدرس electric vehicles عندنا بالجامعه. شكرا دكتور مهند. والدكتور أحمد وسارة يعطيكم العافية وكل عام وانتم بخير.
يعطيك دكتور يعني thank you very much for your nice words. I'm not that expert but yeah, I enjoyed that teaching, you know, the course and doing research in it as well. So do you see my screen?
Yes, we do. Go ahead, Dr. Muhammad.
Okay, nice. So our topic today will be about estimating energy consumption in situations where we have traffic and no traffic, and how to estimate that also accurately when we have some kind of road grade. So the topography of the place where you measure that you know, is a big contributor to that. So the content of this presentation, I'll try to make it, you know, somewhere between 30 minutes and 45 minutes, is about, you know, it's going through 4 sections approximately. We have, in general, I will introduce you to the energy consumption relations, basic physics relationships, and how to model them, or at least the importance of modeling them computationally correctly. And then some calculations based on a very well-known drive cycle. And then we'll go to standard drive cycles in general, how different drive cycles will lead to different energy consumption calculations. Then in the reality, how this, you know, how those standard drive cycles actually reflect in reality. And we did measurements in Amman, Jordan, for that, because, you know, Amman varies in the traffic and as well as in the topography, which is the topic of the next section. So the effect of road grade will be actually first, you know, why it matters. Of course, computation as well, it shows, but some results will be shown. And then also the measurements in Amman, Jordan will be shown as well. And some conclusions will be drawn out of all of these studies. So first, with the energy consumption calculations, as we know, if we want to model the free body diagram of the electric vehicle, we have to look into all forces that affect the vehicle, which include the driving force, that, you know, that's actually the energy that transferred from our tank or the battery to the road. And then it's the opposing forces will be the drag force, the aerodynamic drag, and then the rolling resistance due to the tires with the road, and then as well as we have the gravity. The gravity will of course depend on the road grade itself, which is defined as this angle. The end result will be an acceleration due to Newton's second law. So from Newton's second law, we can build the equations together, and we end up with this force, which is the drive force, should be equal to all of this, where mg, which is ma, is the, you know, status of the acceleration of the car. If the acceleration is constant, then this should be 0. Sorry, if the velocity is constant. All of these, you know, what affects this equation is everything related to all of those parameters. So obviously the road grade, the gravity is, the gravitational acceleration is constant as well. Now the mass or the weight of the vehicle will make a huge effect. The speed cycle, which is the velocity, will make a huge effect, and all of these things related to the aerodynamic drag will actually affect as well. These are, you know, different things that actually car manufacturers compete to reduce, so they can increase the energy efficiency for a specific cycle. So moving forward, calculating the power from the force, we multiply it by the velocity and then divide by 1000 to calculate it in kilowatts instead of watts. We end up with this equation. Now the power if the power applied is positive, it means that we are actually applying a force to the vehicle. So that's a consumed source on the traction, consumed power on the traction. So if the power is positive, we have a traction force on the vehicle. So from the car to the, to the axle, to the tires, the road. And then if the from that equation the power is negative, then we actually are applying brake, which means that we are reducing the acceleration of the vehicle by absorbing some of the kinetic energy through the brakes, which mostly goes to the heat as well for conventional vehicles. And costing means that the power is zero. We are just not pressing any thing on the acceleration pedal. The energy is the integration of the power. So if we have the first case, which is traction energy, we integrate it, we get the traction force, we integrate it, we get the traction energy, positive. If the driving power is negative, we integrate it and multiply it by another negative, so we end up with a braking energy that is positive. But we know the flow of each energy, where it goes in kilowatt seconds. So if we want to transfer it to kilowatt hours, we just multiply it by 3600. We'll end up with kilowatt hours. Now, for the computational modeling, I prefer MATLAB myself. So, but you can do it anywhere you want to solve that differential equation. Of course, I also like to solve it numerically rather than analytically. So I'm using vectors for that, but the model will be is using two inputs. So the vehicle specifications related to mass and tire resistance, aerodynamic drag coefficient, and the frontal area of the vehicle. These are inputs from the car manufacturer. You can actually search that in the spreadsheets from the manufacturer or from people who research that. And then you have velocity versus time, which is something which we call drive cycle. It's either standardized or measured. Everyone who goes a trip now from point A to point B has his own unique drive cycle. So that will be the input to the system. So we compute the driving power. If the driving power is positive, means that we can proceed and compute the traction energy. And if at the specific point the driving power is negative, we calculate braking energy. Now, of course, you accumulate that. So, for every step you do, you accumulate the traction energy, you accumulate the braking energy as well. Now, you end up, after the cycle ends, you end up with a total traction energy, which is the last point, and then total braking energy as well. In kilowatt hours, I will keep that unit throughout the presentation. Now that gives you the total energy, maybe the difference between them, or only the traction energy. The traction energy is something that we consumed anyways. The braking energy is something that might be lost if you don't have regenerative braking, like in the hybrid and electric vehicles. But in conventional vehicles, of course, we lose them as heat. For fair assessment, we go and calculate that per kilometer. So we integrate the velocity, we get the travel distance overall, we divide the consumed energy. It's either the traction energy or the traction energy minus the braking energy divided by the travel distance. We end up with kilowatt hours per kilometer, and that's a universal kind of unit that even car publishers or car manufacturers publish to brag about their efficiencies. So to test that, we applied that to a very well-known cycle, worldwide harmonized light vehicle test procedure. It's basically just speed versus time. And it's standardized. So people, when they test their cars, usually they use the nanometers to apply this speed and then measure the efficiency out of that. I'm using everything computationally, so I'm not doing anything practical here. but I'm trying to compare with practical results at the end. So if you integrate that and find the distance, you'll find it is 23.26 kilometers. I'm assuming that I'm reaching those high velocities. It has several classes. The WLTP has different cycles, WLTC 1, 2, 3, and then A and B. So I'm assuming that I'm reaching B. Actually, I'm taking also, I took data points from the sources for class 3B, which covers this distance, which we will need to calculate later on. Now, if you do calculate the force, calculate the power, calculate, integrate, and find the energies, the traction energy and the braking energy, you end up with these curves. What we care about here is the last point. Oh, by the way, I used the Toyota Corolla 2021 parameters, took them from the internet. And then you'll find that the traction energy is 3.4. Of course, this is I chose the conventional vehicle, so I will not have any use for the braking energy to save something back somewhere. So easily you can find that energy consumption will be whatever the final consumed traction energy divided by the travel distance, which is 0.146 kilowatt hours per kilometers, which is fantastic, when you calculate that. But that is, not the real, energy that you consume. That's only the kinetic energy that could reach the road. But actually, in the way to reach the road, you lose about 75. Well, you start with a point where you will deliver only 25% to the road. So this is only 25% of the actual energy that is consumed. So we don't have any recovered energy, as I said, and car efficiency itself is, by average, they always publish it as 15 to 35%. The average is 25%. So you divide by 25% to see what energy you apply before the engine, before everything. So you'll end up with 0.585, let's say 0.6 kilowatt hours per kilometers. And that's what makes the, the conventional vehicles a little bit, less efficient than electric vehicles, say. Now I'm comparing that with electric vehicles. I'm skipping the hybrid. So I'm taking about the same class of a vehicle. So 2021 Tesla 3 standard range, which is about, I think, 54 kilowatt hour battery size. So and the weight, I think, is 1,650 kilograms. Now the applying the same procedure, same everything, just different car parameters, same cycle as well, the WLTC 3. We end up with these two curves for braking energy and traction energy. So if you calculate based on traction energy, assuming you don't have any regions in braking, you'll end up with 0.168 kilowatt hour per kilometer, which is actually higher consumption than the Toyota Corolla, purely due to mass, actually. Only due to mass. Well, there is some difference also in the aerodynamic drag coefficient as well. But it's for the favor of Tesla, but Tesla is way way heavier. So that's why it will consume more power or more energy. And then the difference happens when you actually trace back to the battery. Actually, you don't lose much going from the battery to the road. So the average is 90%. It could be lower, it could be higher. I took the average. So 90% efficiency. So we divide the traction energy by 0.9 to get what energy actually left the battery. And then I also save about 70% of the braking energy. So whatever we have here, 0.75, I'll take 70% of it that goes back to the battery, which is also a realistic assumption, assuming the driver is not a, it's not a hectic driver. So, so you'll end up with, you lose some due to efficiency, you save some due to braking, you would end up about the same number, 0.164 kilowatt hour per kilometer. Okay, what Tesla publishes is that they have 0.15 kilowatt hour per kilometer, but actually for a different drive cycle. So let me talk a little bit about drive cycles. So because I randomly actually at the beginning chose the WLTLC But then when I looked at the things, so it ended up to be quite different when you apply other cycles. So we talked about the WLTC, which is in the blue here. The other ones that are also kind of universal, especially in North America as well as in Europe. So the FTP, the Federal Test Procedure, I think, and then Highway Field Economy testing. So these two usually, well, before a specific date or specific year, probably 2008, it was these were two different tests. So and when they publish the energy consumption for a vehicle, or let's say the miles per gallon, as they have two numbers, one in city and one on the highway. So the one in city actually is done with this procedure, and then the highway is done with this procedure or this cycle. And after that, especially with the hybrid and with the electric vehicles in there, the EPA decided, the Environmental Protection Agency, they decided actually, they all belong to EPA. Well, not the WLTC, but FTP and HWFET. They all belong to EPA, and they decided to use both of them, and we've added also testing procedures related to how, the air conditioning using during cold weather and hot weather and all that. So without going into too much details, that's introduction to three driving cycles that I will be looking at. So of course they differ in terms of the distance that you can travel within them. You will end up, the blue, we talked about the blue before, the WLTC. For the I wrote in here, okay, the FTP 75 and highway, the green and the red, actually they end up with the same equation. So 90% efficiency, 70% of the vehicle energy is recovered. You end up with 0.147 and 0.151 kilowatt hour per kilometers for these two things. And I'm glad to see actually that Tesla actually published that it's 0.149. The EPA testing, their EPA testing is 0.149 kilowatt hour per kilometers. So so at this point, I'm trusting my model. That's the point that I'm trying to reach here. I'm trusting my model, computational model. So, but still, those are standard drive cycles. So in reality, things are different, and the reason is that habits of driving are different. That's one of probably the major reasons when you talk about different cities or different countries as well. If you drive here in Amman or drive in Chicago or whatever in Europe, you'll find very, very different culture in driving, or actually even the infrastructure is kind of different. Cycles, circles. I mean, we have lots of circles in Amman. We have depends also traffic lights, the patterns of the traffic lights, the speed bumps. All of these make big difference even before touching the driver himself. Different drivers, of course, will make it different. So if you are talking about the same city, let's say same place, still cycles differ anyway, because we have different trips. Points A and point B are different. So we have different paths even for the same point A and B, which we sometimes purposefully do to avoid congestion. And then different driver, even if they have exactly the same point A and B and same path, different drivers, have different driving habits, hard braking or fast acceleration or whatever, or hard acceleration. And then different traffic. So even if you are the same driver, driving in the morning is different than driving in midday, and so on. So, and different circumstances. Obviously, you don't know when you are going to hit the brake anyways. You're not going to repeat the cycle. It's impossible. Circumstances, and that's it. Construction, let's say, happening today, not yesterday. So all of that. So to investigate on average, well, I didn't take an average, but at least I made some investigations. Some driving cycles in Amman, Jordan are measured using an app, actually, GPS logger. The latitude and longitude data are collected every second. Also, actually, it provides the speed as well for every second. So, and gives me the altitude, which I will actually use later for studying the grade, the road grade effect. So, but until now, we are always assuming flat road. So, so I chose a path going from point A to B to C to A again. So just to make it a little bit fair, especially for the study of the grade later on. So point A was actually Duwar al-Waha, and then point B was Duwar al-Shab, point C was Swaleh, point A again Duwar al-Waha. So I'm coming back to the original point. So this cycle, what you see here is actually light traffic, which I took just before sunrise, right before sunrise. Well, not in Ramadan. Then Ramadan before sunrise, maybe it's maybe you'll have some traffic. I don't know, but not in Ramadan before sunrise or just after sunrise, before the people start going to their work, you will have very light traffic. So whatever breaks that you have, usually it's due to the transportation system. It's I mean the infrastructure itself. You had to do a break for a traffic light or speed bump or a circle somewhere, or to stop. Okay, the travel distance for that trip or for that cycle is 17.06 kilometers. Applying that to the computational model, you have 2.4 kilowatt hour consumed as traction energy and 0.46 kilowatt hour consumed as braking energy. And you can see that braking energy is not as a percentage. If you see it, it's less than 20% of the traction energy, which means it's a light traffic. So applying the same equation where you have 90% efficiency of the drivetrain, electric vehicle drivetrain, and then 70% of the electric of the braking energy is recovered, you'll end up with this number for energy efficiency, which is of course I'm using the same numbers of Tesla as well. I didn't drive Tesla. I just made with my own car, which is not Tesla, but the drive cycle applies. When applied to Tesla and computationally, you end up with 0.14 kilowatt hours per kilometer, which is actually lower than the EPA results. Again, this one is very light traffic. So now, if I did the same study, same points, A, B, C, D, A, B, C, A, but during peak hours. So of course, this changed. So I have point A, point B, point C, point A back again here. Actually, the average speed is below 40. It's actually even below 30. Not like the other one. The other one is about 45 to 50, the average speed. This one is about 30 or less. Even though these are the same paths, not only the same point, same path exactly, and same driver, me. So of course, you can see that I took way more different time, actually twice the time or 2.5 the time took with light traffic. Again, plug it in your the computational model, you end up with this these curves. Obviously, the traction energy increased. It was 2.4. Now it is 2.8 something, which indicates that you actually hit the acceleration pedal too much times or more heavily. Of course, because you already hit also the braking pedal too heavily as well, which makes the braking energy 0.976 compared to 0.4 something in the previous case. So there is more braking energy, which means more traction energy. So if you assume that you recover 70% of the braking energy, again, drivetrain efficiency of 90%, you end up with 0.148. And that's a peak hour. That's a peak hour. Now, there is a major point here, which is you don't really recover too much braking energy in very low speeds. You don't. Okay, so I will be generous if I give actually 50% instead of 70% of the braking energy being recovered. It's So this assumption is wrong. So here the assumption is wrong, even though it's higher than the 0.14 that we got with the light traffic, but still actually it's even higher than that. So just by changing the recovered, the percentage of the recovered break-in energy to 50%, you end up with 0.16. So comparing 0.16 to 0.14 or 0.145 or whatever, you will have about 10 to 15% actually increase in energy consumption overall due to traffic. Okay, so that's the conclusion. Heavy traffic can contribute to an increase of energy consumption up to 10 to 15%. Okay. Now I'll proceed to the road grade studies. So the road.
كمان قال 4 ولا 4.5.
Okay, can we mute Dr. or Engineer Mu'taz? I will mute you. I don't have the power to mute anybody with Sarah. Okay, okay, because somebody was talking. So, so road grade matters big time. And why is that? Because it's actually part of the equation that we developed for the computation, for the, you know, free body diagram, for power calculations, and which ends up with for energy calculations. For all the previous slides that I did, that I showed, I only assumed flat road, so theta was 0, and the term related to that, which is mg sine theta, was 0 as well. Now things will change here because I'm actually putting it within my study. So road grade is defined usually as tan theta, but at low, you know, road angles, tan theta is actually equal to theta, which is actually also equal to sine theta as well, approximately, of course, within, you know, within 1% error, so 1%, 2% maximum error. So, and this is where the one that I was talking about. We have a term for gravity effect. So the gravity effect, of course, related to the acceleration of gravity and the mass, and of course, the road grade here. So now I'm including that in my studies. Well, probably I should make some animations here, but okay. So I'm doing a comparative study here to see the effect of positive grades and negative grades compared to flat roads. So positive grade means, you know, inclined upwards, theta is positive, which is also, you can hear it as rising roads or ascent, the ascending road. The other way around, negative road can be also, you know, represented as inclined road or falling road or descent. The cycle that I'm applying everything to is the FTP 75, and the blue here represents the flat road, and this is why I included, you know, I'm writing 0% grade, so theta is tan inverse 0, which is 0. Okay, the flat road. So which we studied before, and it was 0.147 kilowatt hour per kilometer, the energy consumption based on a Tesla car and that drive cycle. Now, if we assume a constant positive grade, so always rising all the way for the entire trip of the 12 kilometers, all the way you are always rising at a rate of 2%, which is a 2% grading, road grade. The computational model gave us 0.239 or 0.24, let's say, kilowatt hour per kilometers. So which is about 70% increase in the 70, probably 75% increase in the consumed energy. That's a big deal, of course, huge. I mean, there we were talking about the traffic and different cycles. We are varying between 10 to 15% up and down only. Now, just suddenly, just 2% grade, and 2% grade is not bad, not too bad, but you know, in a city like Amman, that's kind of, you know, you can see that. Of course, what is non-realistic here is the assumption that this grade exists for the entire trip. It doesn't. Okay. and realistically, you'll go up and then fall down, go up and fall down. Now, if you have the falling road, so the grade is a negative 1.2%, so minus 2% grade, you'll have, of course, the braking energy, you actually hit your brake more often because the car is moving by itself due to the gravity. So you'll have, you're not going to spend too much energy to go from point A to point B, so 0.06%. So, going from point A to point B over over a falling 2% grade of the road actually consumes about 1/4 of the power if you actually go for the same trip, but positive 2% grade rising. That's the conclusion that we get here. Again, there are some non-realistic assumptions, but it is important that we establish this, as why it matters that the road grade should be included in the calculations. So what does that mean in the model? We had two inputs, the vehicle specifications and the speed versus time, the drive cycle. That's the standard. People do that all the time, except for minority, not from car manufacturers, from researchers who actually also include the grade versus time. So our study is complete for energy consumption. So I'm adding grade versus time. So there is nothing about, there is nothing standardized about grade versus time. You will not find standardized data for grade versus time, like the speed versus time. This is something that we'll go to, that we'll measure. The rest of the model stays the same. This is the only thing that needs to be different to modify the computational model, so it will include the effective grid. So the topography in Amman, if I'm living in a different city, or let's say if our city is flat, which is, most of the cities in the world probably are flat, but Amman is heavily populated and has traffic, and actually the topography includes lots of uprising and downfalling road grades. So and that's the demonstration of it. So you can actually simply go from there's no scale for the distance, but I would imagine you go from here, let's say from this point all the way through the roads to this point, which is something that actually I do. I live somewhere here, and then I go to Zarqa to visit my family, and I go through from Istiqlal road. So from this point to this point is actually about 10 kilometers. So if we just assume that for that 10-kilometer trip, if you read the change in altitude, you'll find about 240 meters falling. Fall from point A to point B, which corresponds actually to an average of 2.4%, downfalling. Of course, if you go the opposite way around, the other way around from point B to point A, point B to point A will be positive 2.4%. Point A to point B will be negative 2.4%. So it's an easier drive, less consumption. Okay, so that demonstrates how important it is. Remember that the results that I showed in the previous slide are showing actually 2% and negative 2%. So I'm not far off the assumptions for the topography in Amman. So 2.4% is very realistic for Amman. Okay, so I collected some driving cycles using the same app. So latitude and longitude and altitude data are collected each second. And then we have two cycles now. So we have the speed cycles, which I showed before, and we have now the grade cycles. Now, to avoid non-realistic scenarios, which is going from point A to point B and then say, oh yeah, we save Amman, you save energy in Amman. No, I have to go back to the same point, same altitude. So actually whatever rise and fall I have within the way is within the way, and that's it. But my starting point and last point should have the same altitude. Myself, I chose to have them the same point. But for fair comparison or fair study of the effect of rod grade, you have to start and finish with the same altitude. Okay. Again, I use the same trips. I purposefully used, you know, when I did this testings for A, B, C, and A, I had this in mind that, you know, point A to point A through that cycle will be fair enough for road grade investigation as well. So the for the light traffic case, so remember we have two cases. The light traffic case, the road grade you know, was going up and down, up and down, up and down here. So the last one here, I think, was this positive. Okay, well, so Swaleh is somewhere. Yeah, Swaleh is somewhere here, I think. Okay. So the average, so I'm not showing RMS values. I'm actually showing absolute values of grade, but I'm then calculating RMS value of it. So the grade is varying. It reaches sometimes something above 3% or 4%, sometimes less than 2%, minus 2%, most of the time in between. Within the computational model, the positive effect will be different, totally different than the negative effect. For us to understand how much this variation means, I'm showing an RMS value, so which is about 2.15% for that trip. The energy consumption calculation, based again on 90% drivetrain efficiency of the car and the 70% recovered from the braking energy, we'll have about 0.174 kilowatt hour per kilometer, which is actually about 20% increase compared to the flat road. Okay. So it does affect even if you start and finish with the same altitude. Now for the grade versus, sorry, for the heavy traffic case, of course, it's a longer period. Again, we end up with a little bit different. So I'm assuming that this is a numerical error, computational error. It can be 2%, so it can go up to 2.2%. We had 2.15, it's 2.11 in this case. I'm not sure how it is affected, but I'm assuming we have some errors in altitude, in calculations or collection in the GPS logger. So in any case, let's see the effect of that. Of course, the speed is way lower in these cases. We have energy consumption of about 0.145 kilowatt hour per kilometer. Okay, that's surprising, of course. So lower traffic, you go up and down, and still you end up with the same energy consumption as if it is flat road with no traffic. Again, the vital point here is that you don't collect too much energy consumption, even if you are downfalling, but at speed of 20 kilometers per hour, you don't collect much energy consumption. Yes, you don't spend energy because you just release the pedal and it will fall by itself, but you are not collecting too much energy. You are collecting a small percentage. So I'm assuming 50% of the braking energy being collected. It actually, in this case, it should be assumed probably lower than that, or should be modeled. So there are some modeling for that as well. Should be included in the models as well. So you'll end up with 0.16 kilowatt hour per kilometer, which is again higher than the flat road anyways. Okay. So the conclusion is that, for Amman, Jordan, the road grade is about 2% RMS value, falling or rising. I mean, you might expect an increase in consumption up to 10 to 20%, based actually on the first result without traffic. So without traffic, I'm avoiding traffic, but still getting, due to grade, I'm getting more energy consumption. So the summary, our takeaway conclusions from all of these studies, that you always start with an accurate model to study the consumption. And actually, car manufacturers do that all the time, specifically for aerodynamic drag and for drivetrain efficiency, sometimes for reducing the mass as well of the vehicle. You can use that model to draw many, conclusions based on standard cycles, or if you prefer measured cycles, that would be fine as well. At the end of the day, the comparative study is the most important thing, and not the absolute value of what you get from a drive cycle compared to another drive cycle. No, from a situation to another situation. So you can study the weight, the effect of frontal area, drag coefficient, internal efficiency of the drivetrain, region brake efficiency, which is something that probably is very important in these cases. All of this is not studied here, but you can actually include them in the computational model and do the comparative studies. We did in this study, we did see the effect of traffic, which affects the drive cycle on a flat road, and then road grade, which shows the the effect for specifically for Amman Jordan with realistic or measured results. We demonstrated that traffic can contribute up to 10 to 15% increase in energy efficiency, energy consumption, and then road grade might contribute to about similar number, 10 to about 20% energy consumption. More data can be collected. Accuracy of collecting the data might be an important factor here as well, because GPS data are not always, stable, especially for small distances, collecting data every 1 second and all that. Okay. Now, if you want to go to another city, you can make a different study. You collect new data for that different city because the habit of driving in that city, the topography of that city, and all of that are different. So you can repeat that. Conclusions might end up to be about similar, but accurate conclusions, especially if we are talking about transportation system, let's say buses, let's say trucks, or all of that. Actually, that might be a big deal. That has to be done for every city by itself. And that's it from my side. Thank you very much.
Thank you, Dr. Muhannad, for your great presentation. Now we will open the door for questions and discussion. So anyone have a question, please raise your hand, or you can just open your mic and go ahead. Any questions?
I think yes. Tahani is talking, or
Florian?
Yeah, Florian Ringbeck here from RWTH Aachen University. So you've shown the different energy consumptions for different vehicles, and we could see that there was an impact of the additional weight of the Tesla Model 3 on the consumption. So now my question would be regarding especially bigger vehicles and, to be more specific, SUVs. So at least here in Europe, we see a trend still that the people are more and more buying suburban vehicles, so bigger vehicles with a bigger cross-sectional area in the front. So do you have an idea of how much the energy consumption is increased when you go from a medium-sized car to a bigger SUV? So what the range of energy consumption difference is?
Yeah, I have an idea, but you might need to excuse me about the accuracy of the number. So if we add both, so the mass and the frontal area, so assuming the frontal area is multiplied by 1.5, the mass probably is multiplied by 1.25, you might end up actually about 70 or 80% more energy consumption. I had those studies somewhere, but they are not here now. They're not really, they're not ready for this presentation, unfortunately. But I had those studies somewhere. So, okay, so about 70 to 80%. Yeah, no problem.
Thanks a lot.
Thank you. Questions, please.
Could you hear me?
Yes, yes, I am.
Please go ahead.
Thank you, Dr. Mohamed, for your great presentation and your presentation content. It was so diverse and elaborate. And I have actually two questions regarding the main equation. If you can go back to your vehicle dynamic equation, please.
This, oh, sorry.
No.
Is
Yeah,
this good
one.
enough, or you want to go to the forces?
This is one. This. Oh, yeah. It's better to go back to the forces. Okay, that's good. The first question regarding the tire rolling resistance. Firstly, you use a constant friction factor for the rolling resistance. And I would like to ask, as you know, there is other tire models, non-linear model like brush tire model or magic formula. Did you have the chance to check this non-linear model and see the effect in your model? Does the effect too much on the result or not? Because yeah,
you are right. It's a constant. You know, the effect of the rolling resistance will be huge, especially for low traffic, because for light traffic, because it is a constant thing that is applied all over, you know, regardless of the speed. So I agree with you, but I didn't do that study.
I see. The second question, also for the rolling resistance, as I saw, just to make sure you are focusing on the low grades, because I was expecting to see this term multiplied by cosine theta, but I think, do you assume it's 1 because you have low grades?
Yes. I'm not including the grade in the equation of the tire resistance.
Okay.
Of the term. Yes.
Okay. These are my questions. Thank you for the answers.
Well, yeah, thank you for the questions, actually.
Thank you, Engineer Ayham. Any other questions, please? You can raise your hand, open your mic, and go ahead. So, Dr. Bashar Qawasme, please go ahead.
Assalamu alaikum rahmatullah.
Really
very nice presentation. Thanks, Dr. Muhannad. My question, I sent it on the chat. It's nice that you consider to take the grade or the level grade as one of the parameters. But my question was, why just the plus and -2 grade levels? Why didn't consider more grade levels? And my second question, you mentioned something about for small angles, theta, and that the sine theta, you did this in order to get a linearized model?
Okay, well, answering the first question, yeah, I didn't consider it just because, you know, my purpose was just to demonstrate that the effect of the grade, even for small grades, is huge. The trend is there, so higher grade will mean a huge energy consumption in the rising case, and probably zero energy consumption. Maybe just you are only collecting break-in energy if it is, you know, falling all the time. Like if you go to the Dead Sea, for example, you collect lots of power, lots of the for a big section of the trip. So, but coming back will be just different. So the trend is there. The case of the why the approximation? No, it's not because of linearization. At the end of the day, I'm actually collecting all the data and calculating theta at each point or between every 2 points. So there is no point there, but the definition sometimes of broad grade differs. It's universally known as tan theta, but some people approximate it as theta. Because the term in sine theta is in the force, you know, equation is sine theta. I just wanted to give an idea that 2% will be 2%, which will be 2% again in the equation. That's what I wanted to say, but not for my models. I didn't linearize anything at the end of the day.
Okay, thank you, Dr. Mohammed.
No
Thank you.
Thank you, Dr. Bashar. Any other questions? Also, I would like to remind you to evaluate our workshop for today via the link that has been sent already in chat. Going back to the questions, any other or any further questions, please go ahead.
Excuse me, I am talking again. I have another question.
No problem, I have.
Yeah, sorry. In your model, you used also some constant parameter like the whole vehicle efficiency for the electric vehicle and for the recovered braking energy. Also, you use the constant value. Do you consider to use, let's say, full fidelity models for the recovered energy, like for the regenerative brake and for the electric powertrain to be included in this test cycle, drive test cycle in the future?
Yeah, of course. So thank you again for your question. So your questions are just going to enhance my my things going forward. But including the efficiency things, we're not critical here, because again, I'm doing a comparative study. So I'm only changing one parameter, so to see the effect of that thing, assuming everything is the same. Now, I agree with the energy, regenerative braking collection. That efficiency has to be included even for this study, because it's a big deal. It relies on the speed, it relies on the time given for the brake as well. So it has to be included to enhance the model. So the conclusions here cannot be absolutely accurate, taken as it is, because in reality those things vary big time. They might vary from 70% down to 10%. Actually, now for the drivetrain efficiency, it's good to include them. Definitely better than not including them. But then you have also to include other factors as well. That the current temperature, the how much it was, how long were the drive, because that will affect the efficiency of the drive itself. The temperature of the battery itself, the status of the battery itself might have some effect in the efficiency of the release of the energy from the battery, and all of these things. And if we want to be even more fair, to get an accurate number, we have to include some other factors like the air density as well, which depends on the humidity and and the place, of course, but the humidity and the temperature and the height as well, where where you are collecting the data. So there are many factors that actually change the numbers as numbers, and the purpose was not exactly the numbers. The purpose was mostly the conclusions that we get from a comparative study. But yeah, I like this, and I will take it into consideration, inshallah.
Inshallah, thank you. I see your point. Thanks, Dr. Adham, Dr. Mohammed.
Thank you, Engineer Ayham. Any further questions, please go ahead. So it's yes, Mr. Muhammad.
Assalamu alaikum.
Alaikum.
Salam alaikum.
Dr. Muhammad Dado, I'd like to ask a question about the traffic lights effects, and slowing down to stop at the traffic light and waiting for the sign and starting the game. Did you consider such scenarios?
I'm afraid I couldn't hear very well. You mentioned something about rising and falling, but I couldn't understand the question.
About the traffic lights, about traffic signs.
Write down your question via chat, because we cannot hear you very well. You are opening the adhan, so we cannot hear you, unfortunately. Please write it down on chat, please. Any further questions for the meanwhile?
Excuse me.
Yes, we can. Yes.
Yes, I'm asking about the effect of the traffic light. When you stop at the traffic light, waiting for the sign to open, you are slowing down, stopping the car, then we are starting again. How do you model this effect? I mean, is it considered in your model?
Well, yes and no. So it is not included in my model because the path that I took didn't include. Well, no, it actually included 1 or 2 traffic lights. It did. The path from point A to B to C to A. It has a couple of traffic lights, but it wasn't the focus because the traffic lights are there anyways. Of course, your stoppages will be more, you know, at peak times. So, but those stoppages are not necessarily consumption, especially for electric vehicles. But if we want to isolate them, so they are, at the end of the day, they are part of the drive cycle itself. So when you see a downfall, sorry, not downfall, I mean a decrease in the speed versus time anywhere, it could be a traffic light, especially if it reaches zero. I think this one might be a traffic light here.
Mm-hmm.
That one, it might be a traffic light, but you know, to give you an objective opinion about it, you know, it's very hard because this drive cycle contains many other things. So the person has to, you know, to go through a path, for example, from point A to point B, and then a similar path somewhere else without traffic lights, and then see the effect of traffic lights. Obviously, increasing the traffic lights means more braking and then more acceleration afterwards, which is, regardless of how much you collect from regenerative braking, you lose. So obviously more traffic lights means you know, more energy consumption. But again, my study didn't have that element as you know, a focus point.
Okay. One more small question. In the grade of the road itself, you assumed a constant grade, but actually in real time or real life, you have I mean, horizontal segments, then deep falling, then steep rising. So it is not very simple to consider it as a constant. You have to combine different slopes and also flat segments.
Yes, but yeah, that's what I did when I first showed these results as a constant rise or a constant fall. I was just making the point that the effect of road grade is huge, but then when I proceeded that to collect practical, you know, sense about it, I assumed that I assumed realistic path, which had both. So I had positive grade in my drive cycle and then negative grade in my drive cycle as well. So even if the starting point and the last point had the same altitude, I still had the you know, the effect of road grade. So if I start from point A to point B and finish up with the same altitude, it might come to the mind of somebody that, oh yeah, you didn't end up with an overall reduction of altitude or increase of altitude, so your energy consumption calculations has to be the same. And that's not the case. The case here is that you didn't change altitude from point A to point B, you changed in between, and still the effect of the road grade showed to be about 10 to 20% or 10 to 15% increase in energy efficiency or energy consumption. So it was included in this study.
All right. Thank you. Very nice study, and I'm very interested in it. Thank you very much.
Thank you, Engineer Mohammed. Any last questions? We have already reached to the end of our workshop today. It seems that we don't have any further questions, so allow me to thank you, Dr. Muhannad, for your time with us today and for your great presentation. And I would like also to thank Professor Tariq Totenji, the EcoCar coordinator at HTU. And thank you all for attending our workshop for today. كل عام وأنتم بخير and عيد مبارك. And thank you all for attending our workshop today. Bye.
كل عام وأنتم بخير.
Goodbye.
كل عام وانتم بخير، يعطيك العافيه.
وانت بخير دكتور، الله يعافيك.
كل عام بخير جميعا، الله يعود علينا ان شاء الله بالخير والبركات يا رب.
امين واياكم.